Forget everything you think you know about American air supremacy and the invulnerability of stealth technology. The foundational assumption of American air power that the F-22 Raptor, the F-35 Lightning, the B-2 Spirit, and the forthcoming B-21 Raider are effectively invisible to Russian air defense systems is that Russian engineers have been working methodically to invalidate for 25 years. And the deployment confirmed now through multiple independent technical assessments of Russia's S-500 Prometheus air defense complex in operational configurations that have demonstrated tracking capability against low observable targets has crossed a threshold that should generate emergency reviews in every air force that has structured its warfighting doctrine around the premise of stealth penetration. Let me be clear about something that the United States Air Force acquisition community is desperately hoping you will not understand. Stealth is not invisibility. It never has been. Stealth is radar cross-section reduction, making an aircraft difficult to detect and track at the ranges that matter for weapons employment. The effectiveness of stealth depends on the specific radar frequencies employed by the threat system, the specific angles at which the aircraft presents to those radars, the processing algorithms the threat system uses to distinguish low observable aircraft from background clutter, and the specific stealth coatings and structural features of the aircraft in question. Every one of those variables can be addressed through engineering. Russian engineers have not been standing still, having spent years working within the intelligence community's technical assessments of adversary air defense capabilities, and having watched the cycle of stealth development and counter-stealth response play out since the development of the F-117 in the late 1970s, I can tell you that the current moment is not unprecedented. But the speed and sophistication of the Russian counter-stealth investment represents something qualitatively different from what we have seen before. Stay with me, because what I am about to explain will change how you think about the $1 trillion America has invested in its stealth aircraft programs. The S-500 Prometheus, designated by NATO as the SA-21B Growler, is not simply the next iteration of Russia's long-range surface-to-air missile development line that produced the S-300 and S-400 systems. It represents a fundamental rethinking of the engagement architecture. The S-300 and S-400 systems operate primarily in the centimeter wavelength frequency band, the X and Ku bands, where radar cross-section reduction techniques for stealth aircraft are most effective. Structural, shaping, radar absorbing materials, and internal weapons carriage are all optimized to minimize return in these frequencies. The S-500 incorporates a multi-frequency engagement architecture. This is the critical technical departure from its predecessors. The 91N6E Superdome acquisition radar operates in the L-band, a lower frequency where stealth shaping provides substantially less cross-section reduction than at X-band. The 96L6 cheeseboard radar operates in the centimeter band for precision tracking of conventional targets. The combination creates a sensor network that can use L-band detection to cue X-band tracking and weapons guidance, achieving an engagement solution that exploits the frequency-dependent limitations of current stealth designs. Keep watching, because the physics of radar cross-section and frequency dependency are what make this development genuinely alarming rather than simply a procurement story. Before we go any further, I need you to understand why stealth works differently at different radar frequencies, because this is the technical foundation on which Russia's counter-stealth strategy is built. Radar cross-section reduction through structural shaping, the angular faceted design of the F-22 and the blended curves of the B-2, works by deflecting radar energy away from the transmitter at high frequencies where the object's dimensions are large compared to the radar wavelength. At X-band, the wavelength is approximately 3 centimeters. The surface features of an F-22 that are optimized to deflect X-band radar energy are large enough relative to that wavelength to function effectively as intended. At L-band, the wavelength is approximately 20 to 23 centimeters. At this frequency, the relationship between the aircraft's physical dimensions and the radar wavelength changes. Structural features that redirect X-band energy become transparent or resonant at L-band. The canopy edges, the wing body junctions, the engine inlet geometries that produce minimal X-band return generate significant L-band return because the physics of electromagnetic scattering work differently at that frequency. This is not new knowledge. American radar engineers have understood this limitation since the initial stealth design work in the 1970s and early 1980s. The decision to optimize stealth designs for X-band and centimeter wavelengths was made because the threat radar environment at the time was dominated by those frequencies, and because the additional weight and complexity of radar-absorbing materials effective at L-band frequencies would have imposed unacceptable performance penalties. The trade-off was acceptable when Soviet long-range radars in the relevant frequency bands were not integrated with precision tracking and weapons guidance capability. The S-500 changes that equation by integrating the L-band detection capability with a kill chain that can bring precision tracking and engagement to bear on a cued target. The integration architecture, the data links, the processing speed, the targeting algorithms, is what transforms L-band detection capability from a strategic intelligence asset into an operational air defense system. What the mainstream media will not tell you is the classification history that has kept this vulnerability discussion suppressed in American public discourse, while Russian engineers continued to optimize their counter-stealth architecture. The vulnerability of current-generation stealth aircraft to lower-frequency radars has been discussed in specialized defense technical literature for over 2 decades. The 1999 shootdown of an F-117 Nighthawk over Serbia by a Serbian S-125 Neva system, a 1960s design operating in the very high-frequency band, was a demonstration of this principle under combat conditions. Serbian Colonel Zoltan Dani, the battery commander who achieved that engagement, had modified his system's radar operating procedures to extend the detection range against low observable targets by accepting reduced precision in exchange for initial detection capability, which he then used to vector another radar to achieve a targeting solution. The lessons of that shootdown were incorporated into Russian air defense modernization planning. The investment in counter-stealth capability that began in the early 2000s accelerated through the 2010s and has now produced the S-500 in deployable configuration, is the institutional response to that demonstration that stealth is not absolute. Here is what actually happened at Russian air defense test ranges in the Astrakhan region over the past 18 months that has generated the classified assessments now circulating in Western Air Force staffs. The S-500 system, operating in its developmental test and evaluation phase with operational crews under realistic exercise conditions, demonstrated tracking continuity against targets configured to represent low observable aircraft threat signatures. Those targets, manned test aircraft and target drones with modified radar cross-section characteristics, were tracked in a multi-frequency engagement architecture from detection at range through simulated engagement at distances that, applied to the operational aircraft they represent, would provide significant engagement windows. The specific tracking ranges and detection probabilities from those exercises remain classified. The assessment that has filtered into open-source defense analysis through the accounts of defense officials and analysts familiar with the classified picture is that the S-500 represents a meaningful capability against current-generation stealth aircraft that is not addressed by the radar cross-section characteristics of those aircraft as currently configured. But if you thought that was alarming, stay with me, because the implications extend beyond the technical performance of individual aircraft to the entire structure of American conventional warfighting strategy. American military strategy since the 1991 Gulf War has been built on the premise of air dominance achieved through stealth penetration. The concept of operations for a major conflict scenario, whether against Russia, China, or another sophisticated adversary, relies on the ability of stealth aircraft to penetrate adversary air defense networks, suppress or destroy those defenses in the opening hours of conflict, and thereby create the permissive environment that allows non-stealth assets to operate freely. This sequence is called suppression of enemy air defenses, and American air forces have been organized, equipped, and trained around executing it with stealth aircraft as the penetrating element. If the penetrating element cannot reliably penetrate, the entire sequence fails. Stealth aircraft that cannot reach their targets cannot suppress air defenses. Air defenses that are not suppressed deny the non-stealth assets the permissive environment they require. Missions that cannot be executed safely against integrated air defense do not get executed. And when you remove from the American military toolkit the ability to project air power with confidence against a sophisticated integrated air defense system, you remove the capability that has underwritten American conventional military deterrence since Desert Storm. What I have not yet explained is the investment asymmetry that makes the counter-stealth challenge so difficult to address through conventional procurement responses. The F-35 program has cost the United States approximately $1.7 trillion over its full acquisition and support life cycle, according to the most recent Government Accountability Office estimates. The B-21 Raider, designed with counter-stealth detection as a primary design consideration, will cost approximately $690 million per aircraft in current estimates that historical experience with aircraft procurement suggests are optimistic. These are the response options: redesigned stealth that addresses the multi-frequency vulnerability, more stealthy, low observable coatings, effective at a broader frequency range. The S-500 system costs approximately $550 million per battalion. A battalion can engage multiple simultaneous targets. The procurement mathematics of offense versus defense in the stealth counter-stealth competition do not favor the stealth aircraft program when the defense system can be produced at a fraction of the cost of the aircraft it defeats. Russia has also demonstrated willingness to export its air defense technology. The S-400 has been sold to China, India, and Turkey, a NATO member whose acquisition created one of the alliance's most significant internal disputes. The S-500, once it completes operational certification, will be a candidate for export to states that would specifically value its counter-stealth capability. An S-500 export to China would provide Beijing with a counter-stealth architecture specifically relevant to American operations in the Pacific theater. An S-500 export to Iran would change the air defense environment for any American strike operations against Iranian nuclear facilities. The clock is running. The S-500 is in operational deployment. The vulnerability assessment that American Air Force engineers would prefer remain within classified channels has now been validated by enough independent technical analysis that it cannot be contained as a classified matter. Decisions being made right now about the B-21 program, about radar cross-section improvement programs for existing stealth aircraft, about the development of alternative penetration concepts that do not rely on low observable characteristics alone, will determine whether the American air power enterprise can adapt to a world where stealth provides relative rather than absolute advantage against peer adversary air defenses. The trillion-dollar investment in stealth has not been wasted. It has provided genuine capability advantage against every adversary America has fought since 1991. But the adversary America designed those aircraft to fight has been working the same problem from the other direction for 25 years, and the assessment that their work is producing results is not reassuring when you look at what hangs in the balance. What happens in the coming years in this technical competition will determine whether American conventional military power retains the decisive edge that has underwritten the post-Cold War international order, or whether the erosion of stealth's effectiveness compels a fundamental rethinking of how American military power is organized, equipped, and employed in a world where peer competitors have closed the technological gap.